Okay, so in this video, we're going to be doing another one-dimensional momentum problem, Inelastic Collisions 1. A 26-gram rifle bullet traveling 220 meters per second buries itself in a 3.5 kilogram pendulum hanging on a 2.6 meter long string, which makes the pendulum swing upward in an arc. Determine the vertical and horizontal components of the pendulum's displacement. So let's go ahead and start off with a picture. Okay, so here's going to be my ceiling. My pendulum I'm going to just draw as a block of wood. Essentially, it's something that hangs on a string that has somewhat more mass than the bullet. Okay, so the bullet's coming in from this side. We'll call the bullet B. We'll call the pendulum P. Okay, so the mass of the bullet is given in grams, 26 grams. Divide that by 1,000, you're going to get 0.026 kilograms. It's initially going at 220 meters per second, so V1B is 220 m over s. For P, the mass of the pendulum is 3.5 kilograms. That is significantly higher. And the initial speed of the pendulum is 0. It's at rest. Okay, so the bullet goes towards the pendulum, it strikes it, and it gets embedded inside the pendulum, right? So at this point, you're looking at B plus P. They're together now, their masses. And due to the momentum that the bullet gives the pendulum, it swings up to a certain height. And we have to figure out what that height is. Okay, so we can assume that originally the path that the bullet's taking and the original height of the pendulum is h equals 0. But at a later point, it's going to reach this height up here. And what we need to do is find this delta h. Okay, so determine the vertical and horizontal components of the displacement. The delta h will be the vertical displacement, and then the horizontal we can always use a triangle Pythagorean theorem to figure it out. Okay, so I'm going to go ahead and start this with a conservation of energy statement. ET1 equals ET2. And the 2 points I'm going to compare are this point right here where the bullet is embedded in the pendulum and the point where it's at its maximum. And the reason I'm doing that is because here, just before it starts its upswing, it has a certain speed, right? And that's the maximum speed it's going to have. Because as it starts to swing up, it's going to lose its speed till the speed becomes 0. It reaches its maximum vertical height, and then it's going to come back down. So here we have pure kinetic, and up here we have pure gravitational potential. So I'm going to compare those 2 points. So initially I've got kinetic, so 1/2 mv squared, but the mass is the combined mass of the two. So it's going to be mb plus mp. The combined speed, I'm going to call it v2 bp, right, because both of them are moving. Okay, and equals, now the final energy is gravitational potential. So the equation for gravitational potential is mgh. In this case, it's the combined mass mb plus mp times g, and the h that it goes up is that delta h that we were talking about. Okay, so the nice thing about this expression, check it out. You're going to cancel out the mb plus mps, so those disappear. Now, all that we're missing now is v2bp, because we're trying to find h, right? But we're also missing this. So if we find the speed here of the bullet when it's inside the pendulum, we can solve for delta h. It's pretty simple. So in order to find that, let's now just quickly switch to another expression. We're going to solve our conservation of momentum expression. P1 equals P2. So initially we've got just B moving. So initial momentum is mb v1b. And in the end, they're both moving together. So it's a combined mass, mb plus mp close bracket v2 bp. Okay, and that's the final momentum. So let's now isolate for v2 bp. Divide both sides by mb plus mp. So v2 bp is equal to mb v1b divided by mb plus mp. So at this point, just plug in your numbers. Okay, so mb, 0.026 kilograms times 220 meters per second divided by 0.026 kilograms plus 3.5 kilograms. And when you punch that in your calculator, you are going to get that v2bp is equal to 1.62 meters per second. Okay, so now I'm going to take that v2bp and I'm going to plug it in over here. Make sure you square it. Don't forget to do that. Okay, so you have now 1/2 the 1.62 squared, okay, equals g, which is 9.8 meters per second squared, times delta h, which is what we're looking for. So this is really simple. Square this number, divide by 2, divide by 9.8, and you're going to get delta h is equal to 0.13 meters. Okay, so that's the vertical height that it rises with. Now we got to find the horizontal, right? So what I'm going to do is sketch a triangle here. Okay, so assume this is the pendulum, right, when it's at its swing at this point. Okay, so here's the pendulum. We know that's 2.6 meters long. Now, when the pendulum was vertical, it looks something like this, which is 2.6 as well. We know that it rises up 0.13 meters, right? So this is 0.13. It rises up to that point because you've got the block here and then the block here, right? It rises up to this point right here. So the horizontal displacement is going to be this right there. So what is that number? So pretty much look at it from this point of view. This whole green line is 2.6. The little blue one is 0.13. So if you want to know this side of the triangle, the red, it's going to be 2.6 minus 0.13, which is 2.47. Okay, so 2.47 meters is that side. So you have this triangle essentially. 2.47, 2.6, that's a right angle, and you're looking for the x horizontal component. This is Pythagorean theorem. Okay, so c squared is the hypotenuse, a squared, b squared are the other two sides. So x squared is equal to 2.6 squared minus 2.47 squared. Okay, so you're going to get x is about 0.81 meters. Okay, so there's your x displacement, there's your vertical displacement. So summarizing that in the final statement, therefore, the vertical displacement is 0.13 meters up, and the horizontal displacement is 0.81 meters to the right. Remember, displacement is a vector quantity, so you must include a direction alongside your magnitude. Alright guys, that's it for this video. I hope you enjoyed it. Be sure to smash that like button if you enjoyed it, and subscribe to Physics in the Flesh. Other than that, guys, I hope you enjoy the rest of your day. I will catch you in the next video posted tomorrow at 12 noon, 126, Inelastic Collisions 2. What? Wait, who's back to school? Pumpkin pie recipe. Okay, I'll save that for Halloween. Guys, so that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button and subscribe to Physics in the Flesh so you never miss a video from me, which, by the way, I post every weekday at 12 noon. So be sure to be on my channel at that time. Guys, as always, if you missed my videos from the past, be sure to click over there on the right. You'll see some of my latest videos there. And other than that, guys, I hope you enjoy the rest of your day. Peace.